March 29, 1929, New York City. The engineering specifications sitting on William Van Allen's drafting table would challenge everything European metallurgists believed possible about stainless steel manufacturing. American steel workers, preparing to create architectural cladding using methods that contradicted centuries of Sheffield expertise. Through the steam and hammering of Middletown, Ohio's industrial district, Armco Steel was attempting something European experts had declared impossible at architectural scale. No traditional open-hearth furnaces, no acceptance of surface imperfections, no compromise on chromium content that European mills considered adequate. Yet they were targeting mirror finishes that would outlast anything European foundries had ever produced. In European facilities, stainless steel belonged in cutlery, small batches, limited applications, premium pricing only wealthy customers could afford. The Americans were operating with metallurgical philosophy the Europeans had dismissed as naive. Vacuum atmosphere melting, 18% chromium content, continuous cold rolling to mirror specifications. Production techniques that achieved permanence. European traditional methods never imagined possible. 400 miles from Pittsburgh's steel establishment, the most decisive breakthrough in architectural materials was taking shape. Not in superior European craftsmanship, not in traditional Sheffield methods, but in American engineering precision that refused to accept that stainless steel would ever stain. The heated voices carried through the mahogany doors of Walter Chrysler's corner office on the 42nd floor, where blueprints covered every available surface and cigarette smoke hung thick in the March air. William Van Allen stood before the massive windows overlooking Lexington Avenue, his architect's hands gesturing at the skeletal steel framework rising below them. The building that would bear Chrysler's name was already impressive at 30 stories, but Van Allen's vision demanded something unprecedented for its crown. 185 feet of stainless steel spire, Van Allen repeated, his voice cutting through the skeptical murmurs of the assembled engineers. Not painted steel that will rust and stain within 5 years, not bronze that will turn green with oxidation, stainless steel that will gleam like silver for decades without a single spot of corrosion. The numbers on Van Allen's specifications told the complete story of his impossible demand. The Chrysler building required 3,827 tons of structural steel for its framework, but the architect wanted something entirely different for the decorative elements. The crown alone would need 391,881 square feet of gleaming stainless steel cladding, each panel precision cut and mirror polished to architectural standards that had never been attempted in human history. Chrysler's construction superintendent pulled out his cost estimates, the pages already marked with red ink from countless revisions. Traditional carbon steel cost $40 per ton, delivered and installed. This newfangled stainless steel that Van Allen demanded would run $400 per ton, 10 times the price for an unproven material that European experts insisted belonged in kitchen cutleries, not construction projects. The established wisdom seemed unshakable. Pittsburgh's steel giants had built America's railroads, bridges, and skyscrapers using proven methods refined over decades of experience. U.S. Steel's chief engineer had calculated the metallurgical requirements and declared the project technically unfeasible at architectural scale. The chromium content necessary for true corrosion resistance would make the steel too brittle for structural applications, while the nickel additions required for workability would push costs beyond any reasonable budget. From Sheffield, England, came even sharper criticism. British metallurgists who had perfected stainless steel for surgical instruments and premium cutlery dismissed American ambitions with barely concealed contempt. Their telegrams to New York engineering firms carried the weight of centuries of European craftsmanship tradition. Stainless steel required hand-forging techniques developed over generations of guild knowledge. The precise temperature control and atmospheric conditions could only be achieved in small batches under master craftsman supervision. American mass production methods would contaminate every heat, creating brittle alloys that would crack under thermal stress and corrode faster than conventional steel. The European experts had solid technical reasoning behind their skepticism. Stainless steel's corrosion resistance depended on a microscopically thin passive layer of chromium oxide that formed on the surface when exposed to oxygen. This passive layer could only develop properly under controlled conditions with ultra-pure alloy chemistry. Any contamination during melting, sulfur compounds, carbon inclusions, even trace amounts of phosphorus would prevent proper passive layer formation and doom the steel to rapid corrosion failure. Van Allen listened to the technical objections with growing frustration, but his architectural vision remained uncompromised. He had studied the great European cathedrals, where medieval builders had created structures intended to last for centuries. The Chrysler Building would be America's cathedral to industrial progress, and its materials must embody the same permanence. Paint would fade and peel, bronze would oxidize and streak. Only stainless steel could maintain the mirror-bright finish that his design demanded. While the experts debated impossibilities, George M. Verity was already mobilizing his forces 400 miles west in Middletown, Ohio. The American Rolling Mill Company had spent 29 years perfecting flat-rolled steel production, but Verity saw an opportunity that Pittsburgh's giants had missed. His recent acquisition of Sheffield Steel Corporation had brought German patents for Nerosta steel, an 18% chromium, 8% nickel alloy that German engineers claimed could resist corrosion indefinitely under proper manufacturing conditions. Armco's metallurgical team understood that the technical challenges went far beyond simple alloy chemistry. Traditional steel melting in open hearth furnaces exposed molten metal to atmospheric contamination that would poison the chromium-nickel matrix. Carbon pickup from furnace linings would create carbide precipitates that acted as corrosion initiation sites. Sulfur contamination would form inclusions that created galvanic cells within the steel structure itself. Charles Hooke, Armco's chief engineer, had been studying controlled atmosphere melting techniques that could solve these contamination problems. Electric furnaces operating under partial vacuum could heat steel to 2,400 degrees Fahrenheit while preventing carbon and sulfur pickup. Temperature control within 10 degrees would ensure proper solution of chromium and nickel into the iron matrix. Vacuum levels maintained at 25 inches of mercury would prevent oxidation during the critical cooling phase when the passive chromium oxide layer formed. The financial stakes escalated with every technical requirement. Each 60-ton heat of molten stainless steel would cost $24,000 if contaminated and scrapped, more than most American workers earned in a lifetime. The precision rolling mills necessary to achieve Van Allen's mirror finish specifications would require complete retooling of Armco's production lines. Every aspect of the manufacturing process, from raw material selection to final inspection, would need to meet standards that had never been attempted in commercial steel production. By summer 1929, the full scope of Van Allen's challenge had crystallized into a single question that would define American metallurgical capability for generations. Could American engineering and manufacturing create architectural stainless steel that matched German theoretical specifications while exceeding European craftsmanship traditions? The answer would determine whether the world's tallest building became a monument to American industrial leadership or the most expensive failure in construction history. The September heat inside Armco's Building 7 was nothing compared to the furnace temperatures that Charles Hooke was attempting to control. While Wall Street celebrated another record-breaking day of stock prices, Hooke's metallurgical team worked 18-hour shifts in conditions that would have challenged Dante's imagination. The solution to Van Allen's impossible specifications wasn't simply mixing chromium and nickel into molten iron. It was creating manufacturing conditions that had never been achieved in commercial steel production. Hooke stood before the experimental electric furnace that would either validate American metallurgical capability or consume Armco's entire research budget in spectacular failure. Traditional open hearth furnaces that had built Pittsburgh's steel empire were useless for stainless steel production because they exposed molten metal to atmospheric contamination that poisoned the chromium-nickel matrix. Every molecule of oxygen, nitrogen, or carbon that touched the molten steel during the critical melting phase would create inclusion sites where corrosion could initiate decades later. The technical breakthrough that Hooke pioneered required rethinking every aspect of steel metallurgy that American foundries had perfected over 50 years of industrial development. Controlled atmosphere melting meant heating 60 tons of carefully selected raw materials to 2,400 degrees Fahrenheit while maintaining vacuum conditions that prevented any atmospheric contamination. The electric furnace operated under 25 inches of mercury vacuum, conditions so precise that a single leak in the furnace lining would destroy an entire heat worth $24,000. Raw material selection became an exercise in chemical perfectionism that would have impressed European laboratory technicians. Every pound of chromium, nickel, and iron had to meet specifications that exceeded pharmaceutical-grade purity standards. Carbon content could not exceed 0.08% because excess carbon would combine with chromium to form carbides that acted like microscopic rust magnets throughout the steel structure. Sulfur contamination had to remain below 0.03%, as sulfur compounds created galvanic cells that would corrode the steel from within. The melting process itself required temperature control that challenged the limits of 1920s instrumentation technology. Hook's team used optical pyrometers to monitor furnace temperatures within 10 degrees Fahrenheit because temperature variations would prevent proper solution of chromium and nickel into the iron matrix. Too hot, and the chromium would oxidize and separate from the melt. Too cool, and the nickel would remain in suspension rather than creating the homogeneous alloy structure that stainless steel demanded. Each heat produced exactly 60 tons of molten steel with precisely 18% chromium and 8% nickel, chemical compositions that had to be verified through spectroscopic analysis before pouring. The chromium content provided corrosion resistance by forming an invisible chromium oxide passive layer on the steel surface. The nickel content ensured workability and prevented the brittleness that had doomed previous attempts at high chromium steel alloys. But achieving these precise percentages required melting techniques that European small batch producers had never attempted at industrial scale. The vacuum melting process created metallurgical conditions that eliminated the contamination sources that plagued conventional steel production. Carbon pickup from furnace refractories was prevented by maintaining inert atmosphere throughout the melting cycle. Sulfur contamination from fuel combustion was eliminated entirely because electric heating required no fossil fuel combustion within the furnace chamber. Nitrogen absorption that created brittle nitride compounds was prevented by maintaining vacuum conditions that excluded atmospheric gases. Hook's innovation extended beyond furnace chemistry to include controlled cooling procedures that ensured proper passive layer formation. The molten steel was poured into molds under continuing vacuum conditions, preventing oxidation during the critical solidification phase when the steel's metallurgical structure was established. Cooling rates were controlled to prevent thermal stress that could create microcracks where corrosion could initiate. Temperature gradients throughout the cooling steel were monitored to ensure uniform grain structure development. Quality control procedures that Hook implemented exceeded anything attempted in commercial steel production. Every heat was tested for chemical composition, mechanical properties, and corrosion resistance before being approved for rolling operations. Tensile strength had to exceed 80,000 pounds per square inch while maintaining enough ductility for forming operations. Hardness readings were verified across multiple samples to ensure metallurgical uniformity throughout each 60-ton heat. The first successful heat emerged from Hook's experimental furnace on September 23, 1929, creating 60 tons of stainless steel that met every specification Van Allen had demanded. Chemical analysis confirmed 18% chromium content with 8% nickel and carbon content below the critical threshold that would prevent proper passive layer formation. Mechanical testing showed tensile strength of 84,000 pounds per square inch, with elongation characteristics that would allow the complex forming operations required for architectural applications. But producing metallurgically perfect stainless steel was only the first challenge in Van Allen's impossible specifications. The architect demanded mirror-polished sheets that would reflect light like silver, while maintaining structural integrity under New York weather conditions that ranged from sub-zero winter temperatures to summer heat that exceeded 100 degrees Fahrenheit. Traditional hot rolling operations that worked perfectly for carbon steel would create surface imperfections that would trap moisture and salt, creating corrosion initiation sites that would doom the steel to rapid failure. Hook's controlled atmosphere melting had solved the chemistry challenges that European Experts insisted were impossible at architectural scale. American manufacturing methods had created stainless steel with metallurgical properties that exceeded German laboratory standards while maintaining production volumes that European small batch techniques could never achieve. The vacuum revolution that began in Building 7 would transform not just the Chrysler Building's crown, but establish American leadership in advanced metallurgy that would dominate global steel production for the next century. The grinding wheels in Armco's finishing department screamed against stainless steel with a sound that penetrated bone marrow, but Charles Hooke knew that conventional grinding techniques would destroy Van Allen's mirror finish requirements before the first sheet left the mill. By December 1929, Hooke's team had perfected the controlled atmosphere melting that produced metallurgically perfect stainless steel, but the architect's specifications demanded surface finishes that would reflect light like polished silver while maintaining structural integrity under architectural loading conditions. Traditional grinding operations that worked adequately for carbon steel applications left microscopic scratches across the steel's surface that acted like moisture and salt traps, creating corrosion nucleation sites that would doom even perfectly alloyed stainless steel to rapid failure. Hooke's metallurgical analysis showed that grinding wheel contact created surface roughness measurements exceeding 50 microinches, 10 times rougher than Van Allen's specifications would tolerate. Each microscopic scratch provided a pathway for chloride ions to penetrate the passive chromium oxide layer and initiate pitting corrosion that would spread beneath the surface like metallurgical cancer. The American solution that Hooke pioneered required completely rethinking steel finishing operations that had remained essentially unchanged since the 1880s. Instead of grinding away surface imperfections after the steel was produced, Hooke's process would eliminate surface defects during the rolling operations themselves. Continuous cold rolling mills would compress the vacuum-melted stainless steel through progressively smaller gaps, creating mirror surfaces through mechanical pressure rather than abrasive removal of material. The engineering challenges of cold rolling stainless steel exceeded anything attempted in commercial steel production. The high chromium and nickel content that provided corrosion resistance also created work-hardening characteristics that would crack conventional rolling equipment under the pressures required for mirror finishing. Hooke's team designed new rolling mills with tungsten carbide work rolls that could withstand contact pressures exceeding 100,000 pounds per square inch without deformation or surface damage. The rolling sequence that Hooke developed required mathematical precision that challenged the limits of mechanical engineering calculations. Hot-rolled stainless steel sheets entered the finishing mills at exactly 0.25 of an inch thickness, thick enough to provide structural strength, but thin enough to allow the multiple rolling passes necessary for mirror finishing. The first cold rolling pass compressed the steel to 12.5 of an inch thickness, work hardening the surface while maintaining ductility in the core material. Progressive rolling passes reduced the steel thickness in carefully calculated increments that prevented cracking while achieving the surface compression necessary for mirror finishing. From 12.5 to 6.25 to 3 and 1/8 of an inch thickness, each pass increased surface hardness while reducing the microscopic irregularities that would trap moisture and initiate corrosion. The final rolling pass compressed the stainless steel to exactly 1 56 of an inch thickness, thinner than cardboard, but capable of withstanding 50,000 pounds per square inch tensile stress without cracking. Surface quality measurements that Hooke's team achieved revolutionized architectural metal finishing standards that had remained static since the 19th century. Final surface roughness measured exactly 4 microinches, smooth enough to achieve 85% light reflectivity that matched polished silver while eliminating the corrosion initiation sites that plagued conventional steel finishes. The mirror surface was not applied coating that could chip or peel, but was the actual stainless steel surface compressed to optical quality through mechanical pressure. Quality control procedures for the mirror finishing operations exceeded pharmaceutical manufacturing standards in their precision and consistency. Every sheet was inspected under controlled lighting conditions to verify uniform reflectivity across the entire surface. Microscopic examination at 200 times magnification confirmed the absence of scratches, pits, or inclusions that could provide corrosion initiation sites, Surface hardness measurements verified proper work hardening throughout the rolling sequence without brittleness that would cause cracking during installation operations. The first architectural-grade stainless steel sheets rolled off Armco's finishing mills on January 15, 1930, creating material specifications that European metallurgists had declared impossible to achieve in commercial production. Each 4-foot by 8-foot sheet cost $47 to produce, more than a Ford Model A automobile, but salt spray testing showed zero measurable corrosion after 500 hours of exposure to conditions that would destroy conventional steel in weeks. Hook's breakthrough extended beyond surface finishing to include forming operations that would shape the flat sheets into Van Allen's complex architectural profiles. The work-hardened mirror surface had to maintain its reflective properties while being bent, formed, and joined into the decorative elements that would crown the Chrysler Building. Traditional forming operations that worked adequately for carbon steel would create stress concentrations that would crack the stainless steel or damage the mirror finish that had taken months to achieve. The forming techniques that Hook developed required understanding stainless steel's unique mechanical properties that differed significantly from conventional carbon steel behavior. The high chromium and nickel content created strain-hardening characteristics that actually increased strength during forming operations, but only if the forming was performed within specific temperature ranges and deformation rates. Too fast, and the steel would crack from thermal shock. Too slow, and work hardening would make the steel too brittle for subsequent forming operations. Each formed component was tested for dimensional accuracy, surface quality, and corrosion resistance before being approved for shipment to New York. The mirror finish had to remain undamaged through forming, handling, and transportation operations that would subject the steel to mechanical stresses that had never been applied to architectural stainless steel. Hook's quality standards ensured that every piece of stainless steel that left Armco's facilities would maintain Van Allen specifications throughout decades of New York weather exposure. The mirror revolution that Hook achieved in Armco's finishing mills established American leadership in precision metallurgy that would influence global steel production for generations. The continuous cold rolling techniques pioneered for the Chrysler Building became standard practice for all high-quality stainless steel applications, from surgical instruments to aerospace components. American manufacturing had not simply matched European craftsmanship standards. It had exceeded them while maintaining production volumes that European techniques could never achieve. The stock market crash of October 24, 1929, sent shockwaves through every construction project in Manhattan. But Walter Chrysler's commitment to his architectural monument never wavered. While banks failed and fortunes evaporated, the skeletal steel framework continued climbing toward the sky at a rate of 4 stories per week, driven by Chrysler's determination to complete what he had started regardless of economic catastrophe. The Armco stainless steel panels that would transform Van Allen's architectural vision into gleaming reality were already being fabricated in Middletown, each piece precision cut according to specifications that had never been attempted in construction history. Van Allen's secret weapon, the 185-foot spire that would crown his masterpiece, was being assembled in sections within the building itself, hidden from the prying eyes of competitors who were racing to claim the title of world's tallest structure. The Bank of Manhattan Trust Building at 40 Wall Street was nearing completion at 927 feet, while the Empire State Building had broken ground with plans to reach 1,250 feet. But Van Allen's concealed spire would push the Chrysler Building to 1,046 feet, surpassing the Eiffel Tower as the tallest man-made structure on Earth. The installation of 1,048 individual stainless steel panels presented logistical challenges that tested every aspect of construction management that had been developed during Manhattan's skyscraper boom. Each panel had to be lifted to its exact position using steam-powered derricks that could handle the weight while preventing damage to the mirror finish that Armco had achieved through months of precision manufacturing. The panels weighed between 80 and 320 pounds each, requiring rigging techniques that distributed loads evenly to prevent bending or warping during the lifting operations. Weather conditions created installation windows that were measured in hours rather than days, because wind speeds exceeding 15 miles per hour would make the large panels uncontrollable during lifting operations. Rain or snow would contaminate the mirror surfaces, and require complete recleaning before installation could proceed. Temperature extremes caused thermal expansion that affected the precise tolerances Van Allen had specified for panel alignment. Every rivet hole had to align within 1/32 of an inch, or the entire panel assembly would be rejected and returned to the fabrication shop. The mounting system that Van Allen's engineering team developed had to accommodate the thermal movement that would occur as the stainless steel panels expanded and contracted through New York's seasonal temperature range from sub-zero winter conditions to summer heat exceeding 100 degrees Fahrenheit. Traditional rigid mounting would create stress concentrations that would crack the panels or distort the mirror surfaces. The solution required spring-loaded mounting brackets that allowed controlled movement while maintaining weather-tight seals that would prevent water infiltration behind the panels. Installation crews discovered that even human contact could permanently damage the mirror-finished stainless steel surfaces. Fingerprints left acidic residues that would etch the steel surface if not immediately cleaned with alcohol solutions. Tool marks from installation equipment created scratches that trapped moisture and provided corrosion initiation sites. Every worker handling the panels had to wear cotton gloves and use specially designed tools with polished surfaces that would not damage the stainless steel finish. The panel joint sealing operations required weatherproofing techniques that had never been applied to stainless steel construction. Traditional lead-based sealants that worked adequately for conventional steel would chemically react with the chromium in stainless steel, creating galvanic corrosion that would destroy the panels from their mounting edges. Van Allen's team developed new sealant formulations based on synthetic rubber compounds that provided weather-tight seals without chemical incompatibility with the stainless steel substrate. Quality control during installation exceeded manufacturing standards that had been applied to precision machinery rather than construction materials. Every panel joint was pressure tested to verify weather-tight sealing before the installation crew moved to the next section. Surface inspection under controlled lighting conditions verified that the mirror finish remained undamaged throughout the handling and installation process. Any panel showing surface damage or improper alignment was immediately removed and returned to Armco for refinishing or replacement. The concealed spire assembly operations took place inside the building's crown during the winter months of 1929 and early 1930, creating a logistical challenge that required coordination between multiple trades working in confined spaces. The spire's structural framework had to be assembled with tolerances measured in fractions of inches, because any misalignment would be magnified by the spire's height and create permanent distortion in the final profile. The stainless steel cladding panels for the spire required even more precise installation than the building's exterior panels because they would be subjected to higher wind loads and greater thermal stress at the building's apex. Van Allen's perfectionist demands extended to installation details that were invisible to observers but critical to the system's long-term performance. Every bolt and rivet used in the stainless steel assembly had to be fabricated from the same stainless steel alloy to prevent galvanic corrosion between dissimilar metals. Traditional carbon steel fasteners that worked adequately for conventional construction would create electrochemical cells that would corrode both the fasteners and the surrounding stainless steel panels. The breakthrough moment arrived on May 27, 1930, when the Chrysler Building officially opened to the public at 1,046 feet height, surpassing the Eiffel Tower as the world's tallest structure. The stainless steel spire caught the morning sun like a beacon visible from 20 miles in every direction, creating the visual impact that Van Allen had envisioned when he first specified materials that European experts had declared impossible to manufacture at architectural scale. The installation had required 11 months of precision work that demonstrated American construction capabilities that matched the metallurgical breakthroughs achieved at Armco's Middletown facilities. Every one of the 1,048 stainless steel panels had been installed to tolerances that exceeded Swiss watchmaking standards while maintaining mirror finishes that would reflect New York's skyline for decades without measurable degradation. Van Allen's gamble on American metallurgy and manufacturing had succeeded beyond even his optimistic projections, creating architectural immortality through engineering excellence that refused to accept European limitations on American ambitions. The maintenance crew that assembled on the scaffolding outside 1 Manhattan West in September 2024 faced a mystery that would fundamentally challenge everything the construction industry believed about modern stainless steel performance. The building's exterior cladding, installed just 5 years earlier using the latest stainless steel specifications and manufacturing techniques, showed extensive brown staining and pitting corrosion that made the structure look decades older than its actual age. Project manager Sarah Chen documented the failure with photographs that would shock metallurgists across the industry. Stainless steel that had failed catastrophically in conditions far less severe than what the Chrysler Building had endured for 94 years without a single sign of corrosion. The forensic analysis that followed revealed the devastating truth about modern stainless steel manufacturing that had prioritized cost reduction over metallurgical integrity. Contemporary stainless steel contained just 10.5% chromium, the legal minimum required to meet stainless steel specifications, but insufficient to provide reliable corrosion resistance under real-world exposure conditions. The manufacturing shortcuts that dominated modern production had systematically eliminated every quality control measure that Charles Hooke had pioneered at Armco in 1929 and 1930. Electric arc furnaces that melted 60% recycled scrap metal introduced sulfur inclusions and manganese compounds that created corrosion initiation sites throughout the steel matrix. The recycled content that environmentalists celebrated as sustainable manufacturing actually contaminated the steel chemistry with trace elements that prevented proper passive layer formation. Copper contamination from recycled electrical wiring created galvanic cells within the steel structure that accelerated corrosion rates beyond anything that pure virgin materials would experience. Fast production cycles that maximized furnace throughput eliminated the controlled atmosphere conditions and extended melting times that Hooke's process had required for proper degassing operations. Hydrogen trapped in the steel during rapid melting weakened the passive chromium oxide layer that provided corrosion resistance, creating microscopic pathways for chloride ion penetration that initiated pitting corrosion. The vacuum melting techniques that had been standard practice at Armco were abandoned as unnecessary expenses that reduced production efficiency. The comparative testing that metallurgical laboratories conducted between modern stainless steel and samples retrieved from the Chrysler Building's original installation revealed performance differences that seemed impossible until the manufacturing processes were analyzed in detail. Modern stainless steel showed measurable pitting corrosion after 18 to 36 months of coastal exposure conditions, with critical pitting temperature measurements of 15 degrees Celsius. The Chrysler Building's Nirosta steel showed no measurable degradation after 34,560 days of New York weather exposure, with critical pitting temperature exceeding 65 degrees Celsius. The investigation that followed traced the quality degradation to systematic changes in steel manufacturing philosophy that had occurred during the 1970s and 80s as global competition forced American producers to reduce costs through process shortcuts. The 18% chromium and 8% nickel content that Hooke had specified for architectural applications was gradually reduced to save raw material costs, while the controlled atmosphere melting that eliminated contamination sources was replaced by conventional melting practices that introduced impurities that compromised corrosion resistance. Metallurgical analysis using electron microscopy revealed the microstructural differences that explain the performance gap between 1930s and modern stainless steel. Hooke's vacuum-melted material showed uniform chromium distribution throughout the steel matrix, with chromium carbide precipitation completely eliminated through controlled cooling procedures. Modern stainless steel showed significant chromium depletion zones around sulfur inclusions and manganese compounds, creating local galvanic cells that initiated pitting corrosion under chloride exposure. The passive layer chemistry that provided stainless steel's corrosion resistance was fundamentally different between the historical and modern materials. Armco's controlled manufacturing had created dense, adherent chromium oxide films that self-repaired when damaged by mechanical abrasion or chemical attack. Modern stainless steel formed porous, poorly adherent passive layers that provided minimal protection against chloride penetration and offered no self-healing capability when damaged. The American comeback that began in 2024 was driven by engineering teams who rediscovered Hook's manufacturing principles and applied them using 21st century process control technology. Vacuum induction melting systems that could maintain atmospheric purity levels exceeding Hook's original specifications were combined with computer-controlled chemistry monitoring that ensured precise chromium and nickel content in every heat. Ultra-low sulfur content achieved through advanced desulfurization techniques eliminated the inclusion sites that had plagued recycled content manufacturing. The Renaissance extended beyond chemistry control to include surface finishing techniques that exceeded even Van Allen's original mirror finish requirements. Laser polishing technology created surface roughness measurements below 1 microinch while eliminating the mechanical stresses that conventional grinding operations introduced into the steel surface. The passive layer formation that occurred during controlled cooling was optimized through precisely controlled temperature gradients that created uniform, dense chromium oxide films with superior corrosion resistance. Quality verification procedures that incorporated 90 years of corrosion science advances ensured that modern stainless steel would match or exceed the performance that Hook had achieved through empirical methods and engineering intuition. Accelerated corrosion testing using cyclic salt spray exposure and electrochemical polarization measurements predicted service life performance with accuracy that 1930s technology could never have achieved. The philosophy that drove the American comeback represented a fundamental rejection of the cost-cutting mentality that had degraded steel quality over decades of global competition. Building for centuries rather than quarterly profit reports required returning to Hook's principles of metallurgical perfection through process control rather than specification minimums. The premium pricing that quality stainless steel commanded was justified by performance data that showed total life cycle costs favoring superior materials over cheap alternatives that required replacement within decades. The triumphant proof of American steel mastery was demonstrated every morning when crane operators cleaned the Chrysler Building's crown, not from corrosion damage, but from city dust and atmospheric deposits that accumulated on any exterior surface in Manhattan. After 94 years of exposure to conditions that had destroyed modern stainless steel in 5 years, Armco's original installation still achieved its mirror finish with 1 clean cloth and 1 quick wipe. The passive layer that Hook's controlled manufacturing had created continued to self-repair and maintain the corrosion resistance that Van Allen had demanded when European experts declared his specifications impossible to achieve.